Welcome back to Pharma-info with Shubhashish. Today the topic which we have selected is another descriptors, right? The descriptors which is used in 2D-QSAR, that is the steric parameter, or the steric descriptors rather. Okay, we know that a particular compound is having a size, a shape. That means some are found to be very bulky, some are found to be less bulky, right? And all the things are found to be important because it can influence, or definitely it should influence how it approaches the binding site. Okay, it is the bulkiness or the shape or the size which determines that whether the drug can approach the binding site in an effective manner, or it will get stuck. It will often get hindered in accessing the binding site residues and all. So that means it is finally the shape and size which is found to be an important criteria, right? Which is found to be an important parameter, right? Which has to be taken into account while dealing with a particular drug and all. Because ultimately it is the size and shape. Okay, if it is found to be bigger in size and if the receptor active site is found to be smaller in size, so irrespective whether you are just feeding the compound with so many pharmacophoric groups and all, they will not fit. Why? Because it is because of the bulkiness. So this has to be taken into account. How it is found to be a beneficial one, or sometimes it is found to be an unfavorable one. So that means the favorable as well as the unfavorable interactions. Okay, that is related to the bulkiness, at the same time the size as well as shape. So all the things matters a lot. It matters a lot, right? Chalo. So now steric parameters. So they have studied so many steric parameters and all, and after a long time, so they dealt with this particular steric parameters for a prolonged period of time, right? And later on, they have just made it very concise and very short and all. So they have just made few parameters, okay, few parameters which are related to the steric properties of a particular compound, right? So one of the important steric parameters is found to be Tufts steric parameter. Tufts steric parameter or Tufts steric factor, same thing, right? What is that exactly? And symbolically, Tufts steric factor or parameter can be represented by ES. ES, okay? And the equation for this Tufts steric parameter is found to be ES equals to log Kx by K naught. So what is that Kx and K naught? K means definitely there should be a reaction, right? There should be a reaction. That means how we can determine the K? That means we have to run a particular reaction. So here K naught means the dissociation constant or the rate constant of the unsubstituted one. That means we have to see that the standard which they are using for that to conduct this particular study, right? And Kx means what will be the effect of that substituent which is found to be sterically bulkier. It may be sterically bulkier, it may be sterically smaller, right? Okay. Now the thing is that, so here what kind of reaction they have, they are running, right? The reaction is the prototypical reaction that they are just monitoring here is found to be the hydrolysis, the acidic hydrolysis of an ester, and that too an aliphatic ester. So they have taken a standard that is an aliphatic ester, and acidic hydrolysis of the ester is found to be the reaction which they are monitoring. That means whether the hydrolysis is found to be a faster or slower. Okay, for an unsubstituted aliphatic ester, for that particular standard aliphatic ester, okay, we have a particular rate constant. Okay, that means it will follow a certain pace, right? It will follow a certain pace, right? Now what we just want to see, same as that of the earlier one, that what we found in case of electronic parameters, that means in Hammett substituent constant, right? In my last video you can find that one, right? So here the Kx is found to be the effect of substituent. Now if I just replace a portion of this aliphatic ester, standard aliphatic ester with the substituent, whether the substituent is influencing the hydrolysis process, whether it is increasing the rate or decreasing the rate, that we are just trying to figure out, right? Okay, and plug in, and we have to plug in both the values for the standard as well as for the test. We can get the value of ES. So that means ES can be a positive, ES can be a negative, depending on the value that we are going to get for these two things. Like Kx, that means the rate constant for the substituted ester and the rate constant for this aliphatic ester. That means the standard one, right? Okay. But one criteria is there. Whatever substituents that you are going to study through this ES, right? All the substituents, this is found to be one of the, what we can say, the prerequisite, the essential criteria that should be there for each and every substituents, right? What is that? The substituents which are being considered for the study, because we are just trying to monitor the influence of the substituent towards the hydrolysis of that particular ester, substituted ester, right? Okay. Criteria is what? So the criteria is, whatever substituents that are chosen for that particular study, they should interact sterically with the tetrahedral transition state of the reaction. So whatever substituents that you are choosing for that particular, for the determination of ES, those substituents should interact sterically, because we are dealing with steric parameter. They should interact sterically with the tetrahedral transition state of the reaction, not by means of hydrogen bonding or by resonance. This should be the criteria, because if we are focusing on that particular, the latter part, that is resonance or hydrogen bonding, what will happen? Hydrogen bonding and resonance is an example of electronic influence, not the steric influence. So that means the substituent should behave in such a manner so that we can only figure out their steric contribution. It's not that we are not after their electronic contribution, right? So that means here the substituents which are contributing, electronically, those should be excluded from the study. That we can readily get with the pattern with which they are approaching. What? Approaching to the ester, right? Approaching to the ester or approaching to the transition state, right? Which is found to be tetrahedral in nature, right? So now, why it is tetrahedral? Because the thing is that they are monitoring what? Aliphatic ester. Aliphatic ester, its hydrolysis. That means it is the hydrolytic reaction through which we can get the rate constant. Whether the rate is found to be faster in presence of a substituent or it is slower in presence of a substituent, that we are just trying to figure out with the help of ES, right? Chalo. Now the thing is that with that, now let us just bring few examples and all, or the substituents and all, right? Okay. Whether we can get, in which case we can get a positive ES value, in which case we can get a negative ES value, right? Okay. Chalo. So now the substituent, suppose ki the standard ester is found to be like this. Right? For the standard, the X is found to be a methyl. So for the standard, X is found to be methyl. That means ethyl ethanoate. So ethyl ethanoate is found to be the standard ester here, right? Chalo. Now we have to see. So for this we can get a value for this K0. That means K0 for the dissociation constant, or rather the hydrolytic constant, or rather the equilibrium constant of what? The standard. That means the unsubstituted ester. Now let us bring few substituents. Let us find their influence over the rate of hydrolysis, right? Okay. Chalo. So now let us say that, let us bring few atoms, right? Suppose let us bring hydrogen or fluorine. Now you may raise the question that the hydrogen and fluorine, okay, being a smaller one, okay, hydrogen and fluorine both are, hydrogen is an example of a positive one and fluorine is an example of a negative one, electronegative. But in which sense they are found to be same? As we have just at the very initial part of this particular discussion, we have told what? It is the bulkiness, it is the shape, it is the size which has to be taken, which need to be taken into account while dealing with top steric factor, while dealing with the steric parameters and all, right? So that is why hydrogen and fluorine, in which respect they are found to be same? With respect to their van der Waals radii, they are very close to each other. We are not after dealing with the electrons and all. We have to keep it aside, the electronic contribution. We are dealing with the shape and size. Okay, with this particular shape and size, will it be readily accepted by the interactive site or not? That we are just trying to figure out, right? Okay, chalo, in that case, what we can say that, okay, now let us bring the substituent as H and F. We are just trying to see that what will happen when X is found to be hydrogen or X is found to be fluorine. So what they observe, that being a smaller entity, suppose ki fluorine, if we just try to figure out the van der Waals radii for this, you can find it 1.31 angstrom, which is very far more less than that of methyl 1, right? Methyl 1. For this methyl it is found to be large, right? Okay. So what will happen? The steric crowd is found to be, when it is found to be hydrogen, the steric crowd will not be found to be that much. So if the steric crowd is not there, what will happen to the rate of hydrolysis? The hydrolysis is found to be faster than that of the ethyl ethanoate, than that of the ethyl acetate, which has been taken as a standard. So here hydrogen, if it is hydrogen, if it is fluorine, as their shape or size is found to be more or less similar, so that is why they are not occupying a large space. So here the steric field is found to be very less. So that is why it is not found to be electronically crowded. If it is found to be electronically crowded, then only it can hinder the process of hydrolysis. So that means there is no hindrance as such. If there is no hindrance, so what will happen to the rate of hydrolysis? The rate of hydrolysis will get faster. So what will happen if we just plug in these two values, right? The substituted one and the unsubstituted one to that particular equation, what will you get? ES equals to log Kx by K naught. So Kx, X, what we have taken? Hydrogen or fluorine. So what we got here? It is found to be faster. So here it is greater value. Here it is, the K naught is found to be smaller value. So in that case, you can find the ES to be a positive one, right? In a similar sense, if we just increase the bulkiness here. Suppose K, instead of hydrogen or fluorine, let us bring ethyl here, C2H5. Okay, C2H5. So what will happen to that? So now it is found to be larger than that of methyl. So that means here the crowd is found to be more. This area is found to be highly populated. So what will happen? The nucleophile will get some kind of hindrance. So if the nucleophile, which is likely to participate in the process of hydrolysis, if it will get the hindrance, so what, as a result of it, what will happen? The rate of hydrolysis will become slower, making the Kx smaller, just ulta of this, and this is found to be greater than this. So in that case, there is a chance that you can end up with the ES is found to be a negative one. Now, one question here. Okay, so how long we can extend? So whether each and every aliphatic carbon, they are influencing in a similar manner. If we keep lengthening the hydrocarbon chain, can we get the higher, can we get the negative? So whether we can intensify the negative value, is it so or not, right? That we'll see. What I mean to say is, earlier it was a methyl. Now we have just converted the methyl into an ethyl. So we have extended it to another one, right? If we further increase it to C3H7 or even bigger like C4H9, so what will happen? What will be the influence to that? Whether the value will get deteriorated or not to the negative side, because we have seen when it is found to be sterically bulkier, so what will happen to the rate of hydrolysis of the substituted one? The rate of hydrolysis is found to be slower, making the ES negative. Okay, chalo. Now assume that this is found to be, instead of methyl, it is found to be a butyl. So what will happen? Can we expect a negative value is found to be more here? Yes or no? No. Why? Because what happened at the very beginning, what I told? That time I told that whatever substituents that you are just considering for the determination of ES, those substituents should interact sterically with the tetrahedral transition state of the reaction. Tetrahedral transition state of the reaction, right? So tetrahedral transition state of the reaction, that means here a space constraint is there. That means, so here if we just consider this butyl chain, the butyl chain or butyl group, what will happen? This is the carbon which is found to be placed in the proximal vicinity of this particular state, of this particular tetrahedral area, right? Or tetrahedral stuff, right? So here the tetrahedral, this is found to be the what? This is found to be the tetrahedral transition state of the reaction. So here the esteric moiety, that means COO, the principal portion of that particular ester is staying here, right? So that means the substituent which is found to be the proximal neighbor, which is found to be the immediate neighbor, can influence the rate of hydrolysis. Now simply look into this particular chain, right? What will happen? The carbon, okay? Immediate neighbor is another carbon, immediate neighbor is another carbon. Now, if we just try to figure out the distance from this, in between this carbon and this carbon, yes, it is found to be far apart from this immediate neighbor of this alkanoate portion. So here the alkyl group is found to be more, alkyl group is found to be large, right? So it's a huge member, C4 is found to be more than that of methyl, right? Methyl, ethyl. So as it is just far away, this carbon is found to be far away from the center. Suppose this is found to be the reactive center, right? So as this carbon, that means the fourth carbon of this butyl is found to be far away. That is applicable to third carbon also, right? So as they are found to be far away, they cannot influence the process of this hydrolysis. They cannot influence. So the influence, what that means, the influence is solely depends on either a single carbon or a 2 carbon chain. It cannot be extended to up to 3, 4, 5, 6. Okay, that means longer the chain, the effect is found to be less. The influence is found to be less. If you keep lengthening the chain, so what will happen? The influence is gradually depleting. Why? Because they are found to be far away from the center. This is the center which is being attacked by a nucleophile, and we are just monitoring the influence of the neighboring group or atom, right? So we cannot say this is found to be the immediate neighbor. This is the immediate neighbor with which this is connected. So that is, this is found to be far away from this reaction center. So that is why the influence of this carbon, okay, though it is a part of this butyl, as a whole we can call it as butyl, but still this cannot influence. This cannot influence. So that means here the value, you are not supposed to get the value which you are desiring, right, for this. But similarly, if we just put something like this, suppose key like this, okay. If the substituent is found to be like this, in that case what will happen? In that case, all the three carbons, right, they are making that area bulk. Okay, they have just made that area, that means this area, to be more sterically crowded. Why? Because all are distributed around this. At least it is distributed half circle, right? So half circle is occupied by this with this particular 3 carbon. Though it is made up of 3 carbon, but still it is influencing. Why? Because it is the orientation of the alkyl chain. It matters a lot. It is a normal butyl. Now if I just put here tertiary butyl, it is something like this. So the orientation of tertiary butyl and the orientation of normal butyl is not found to be same. In case of normal butyl, you cannot access each and every carbon readily. But in case of tertiary butyl or isopropyl, you can access each and every atom associated, each and every significant atoms associated with that particular entity readily. So it can influence the hydrolysis a lot than that of this. Though they are made, though the elemental composition is found to be same, but the orientation matters a lot. The orientation matters a lot. Okay, so this is about this ES and all. Now let me just deal with the limitation of this. The limitation of this ES, right? What is the limitation? As I said that the groups which cannot contribute sterically, okay, cannot be considered for the study. Okay, that means top steric factor, that means ES, cannot be determined for those substituents which are found to be sp2 hybridized. What do you mean by that? That means if you find an element of unsaturation in a substituent which cannot be introduced in that particular study. What does it mean? Suppose ki that time I brought what? Like H3C, H2C. That means ethyl. I just wanted to see the influence of this ethyl over the hydrolytic process and all, right? So now let me just modify this ethyl to an ethylene. Suppose ki I am just rubbing it off and just transforming the ethyl to an ethylene, H2C double bond CH. It's not possible. The moment it recognizes the ethylene, that means the moment it recognizes this 2 carbon chain as ethylene, not as ethyl, it cannot determine the value of ES. So the value of ES cannot be determined when the aliphatic chain is having an element of what? Unsaturation. That means the pi bond, because the pi bond may participate in the process of what? Process of conjugation, in the process of resonance. So here it is the steric property that is being influenced by the electronic property. So that means you cannot get the sole contribution. So that is why this is the biggest limitation of what? ES. Okay, thank you.